Hey guys, welcome back. This will be the practice test solutions here, or the practice quiz solution. So make sure you're only watching this after you've actually tried it on your own. So assuming that they're independents, what's the probability that a monkey and a kangaroo will fall off the bed tonight? So let me read the first part. It says a troop of little monkeys, that's actually what they're called, I had to look it up, were jumping on the bed. On any given day, there's a 35% chance that there will be a monkey that will fall off the bed. Next door, a mob of kangaroos, I think that's what they're called as well, we're jumping on the bed. Being more adept to jumping, there's only a 20% chance that the kangaroos will fall off the bed any given day. All right, so we've got 35% chance for the monkeys, 20% chance for the kangaroos. Now these are not disjoint events. They're jumping on the bed in separate rooms, but at the same time. So it is possible that both of them there will be a night where both a monkey and a kangaroo will fall off the bed. Now, they don't tell us what that probability will be, but they should be independent of each other. If we have monkeys jumping in a separate room as the kangaroos, one of the monkeys falling off wouldn't change the probability of the kangaroo falling off. So to find the probability of both of them, if assuming they're independent events, what's the probability a monkey and a kangaroo fall off the bed? We would multiply those two together. So 35% of 20% would be 7%. So basically just multiply the two probabilities and that would be it. That's what we can do for the union of two, or the intersection of two events if they're independent events. We just multiply the probabilities. What's the probability that a monkey or a kangaroo will fall off tonight? So we want to add those probabilities, the 35% plus the 25%. But the problem with just adding those together is that that would actually count the intersection of those two twice. The probability that on any night that both of them, one of each of them, a monkey and a kangaroo, would have fallen off. So we have to subtract that overlap, which was counted twice, which is a 7%, leaving us with 48%. What is the probability that a kangaroo or a monkey falls off, but not both? So that's exclusive OR, so we would subtract the intersection twice. So 35 plus the 20% minus 2 times the 7%, which will leave us with 41% altogether. What are the chances that a monkey will not fall off the bed? Well, if the probability a monkey will fall off is 35%, then the fact that they would not be would be 1 minus 35%, which would give a 65% chance. If the kangaroos enjoy this activity every night for an entire week, what's the chances that a kangaroo does not fall off the bed on any of the 7 nights? Well, the probability for the kangaroo was 20%, I believe, yes. All right, so the probability that they do not fall off would be 80% on any given night. So 7 nights in a row of 80% would be 0.8 times to the 7th power, which would be a 20.7 or 97% chance that that would occur. What are the chances that if a monkey jumps 7 nights, a monkey will fall off at least one day? Anytime we see at least one, we should always solve by the complement. So we're going to do 1 minus the probability that 7 nights in a row no monkeys fall off, which would be a 65% chance. So 1 minus 65% to the 7th power would give us a 95% chance. So there's a 95.1% chance that in an entire week of 7 days, at least a monkey will fall off at least one of those days. What are the chances that the kangaroos can get away with jumping on the bed for 4 straight nights until they finally have someone fall off on the 5th night? Well, that means 4 in a row they would have nobody fall off, so it would be 0.8 to the 4th power times 0.2 to the 1st power, because that would be the special event that occurred on the 5th night, which would give us an 8.2% chance. It would be pretty rare for that to occur. What are the chances that a kangaroo can jump 2 nights in a row with no one falling off the bed? Well, 20% chance a kangaroo will fall off, so 80% they won't. So 2 nights in a row, because they're independent events, we can just multiply them together. So 0.8 times 0.8 would give us 64% chance. The monkeys managed to go a whole week without someone falling off the bed. Then one of the kangaroos, of course, because kangaroos talk, insists that they are due for an injury. Another says that they must be getting better at their jumping skills. Do you think that they are due for a crash? Well, this is an example of the law of averages, which is a false law. The law of large numbers is true. So in the long run, it would average out and approach the empirical probability. But we can't estimate short-run behavior when dealing with independent events. Each day is still independent of the next day. So there are no such thing as streaks or due for anything. So law of large numbers tells us that the cumulative relative frequency will converge to true empirical probability in the long run, but we cannot predict short-run behavior. Pretty much what I just said. The law of averages is a misinterpretation of the law of large numbers, saying that we can predict the behavior in the short run, saying that it will balance out in any given short run behavior. or a certain set number of trials. Each day is independent of the next, so the probability remains the same regardless of what has happened for the previous events. Jacob has a bag of his favorite marbles, and in it he has 3 red marbles, 4 blue, and 10 of his favorite color, the orange marbles. What is the probability Jacob will remove a red or a blue marble? Well, the probability of a red marble would be 3 out of 17, and blue would be 4 out of 17, but then we'd have to subtract the overlap. Now, there are no marbles that are red and blue, so they're one or the other, so there is no overlap, so we're subtracting 0. So since these are mutually exclusive, we could just add them together. So that would be 7 out of 17, which you can reduce or change to a decimal or percentage in this case, I suppose, 41.2%. What's the probability if he removes 2 marbles without replacement? So if it's without replacement, the probabilities will change. These are no longer independent events, that he'll get 2 marbles. Orange marbles. Well, the first orange marble would be 10 out of 17. The second one would be 9 out of 16. So multiply those, put them in the calculator, right? It'll reduce the fraction, then we have to convert it to a decimal. If Jacob removes 3 marbles without replacement, again, so they're not independent events, because after each one's removed, it's going to change the overall probabilities. What are the chances he'll get at least 1 red? Anytime you see at least 1, we solve by the complement, so we're going to find the probability he doesn't get any reds out of 3 chances, and then subtract it from 1. So the probability he doesn't get a red is going to be, there's only 3 reds, so that would be 14 out of 17 for the first one. So 1 minus 14 out of 17, but then each additional one, there's 1 less non-red and 1 less marble altogether. So it'll be 13 out of 16 and then 12 out of 15. And we subtract that, of course, from 1 once you find it, and that'll give us that fraction, which once changed to a decimal gives us 46.5%. Jacob has a bag of his favorite marbles, same thing here. What are the chances that if he removes a marble from the bag without replacement, he doesn't get an orange marble until his 3rd attempt? Well, that would mean the first 2 are not orange, which would be 7 out of 17 and then 6 out of 16. And then his 3rd attempt would be special because it actually had to be an orange one, which at that point there's still 10 out of 15 remaining because all 10 of the orange ones were there. Then we would change this to decimal, which would get 10.3%, which is pretty rare. 14. If Jacob removes 3 marbles one at a time and replaces them after each draw. So if we replace them after each draw, it's going to be an independent event because the probabilities are not going to change because there's still going to be 17 marbles and all of them will be replaced and refreshed after each draw. So that'll be different than what we saw with the dependent events or occurring up here when we were drawing without replacement, which is what we normally do. What's the probability he draws at least 1 blue marble out of the 3? So if we see at least 1, that means it could be 1 marble that's blue, 2, or all 3 of them are. So instead of finding those separate probabilities, we're going to use the complement rule. So we're going to do 1 minus the probability that he doesn't get any blue at all, which would be the only way that this doesn't occur. So the blue, there are 4 out of 17, so that the probability it's not blue would be 13 out of 17, and that's going to remain the same for each draw because once we draw one of those 13 out of 17, we're going to replace it. So we still have 13 out of 17 for the second draw, and then we replace it again, which will go back to the 13 out of 17 again, unlike the events that we did without replacement. So put that in the calculator, it'll reduce it for you, then change it to a decimal, which will give you 55.3%. Number 15, an antique boat show, 90% of the boats are made from wood, so that's going to be the marginal distribution and the marginal probability here. 75% are chrome, or have some chrome accents on the boat and at least 1 visible feature, and 68% have both. Well, once we know the overlap here, we can go ahead and subtract here to find the probability that was only wood, and doing that we would have 22%. The ones that only had chrome accents would be the difference here, which would be 7%. Alright, what's the probability that a boat from the show has both features? Oh, I guess we want to fill in the Venn diagram, so go ahead and find the part on the outside as well. So if we add the 90% and the 7, it would be 97%, meaning there's only 3% of boats that have neither feature. 16. What is the probability that a boat from the show has both features, so wood and chrome? Well, they actually already told us that. That was the overlap between those, which would be 68%. What's the probability a boat has chrome accents but not made of wood? So chrome but not the wood part is going to be 7%. So we subtracted those two, the 75 minus the 68, which gave us 7%. What's the probability that if a boat has chrome accents, it is also made of wood? So the probability of wood, given the chrome accents, So the chrome accents was a 75%, and also having the wood, the intersection would be 68. So 68 out of 75%, which is going to be a really high percent of 90.7%. What's the probability that a boat is either made of wood or has chrome accents? So that's going to be the union of the two. We said that was 97% earlier. You could take the 90% plus the 7% of only chrome. Lots of different ways to do it. You can also add the marginal, then subtract the overlap, which is what I showed here, which will give us a 97%. Then, of course, we got 3% on the outside. Are the two mutually exclusive? Well, the intersection is equal to 68%, so it's not equal, so therefore it's not mutually exclusive, because it was possible to have a boat that had wood, that was made of wood, and also had chrome accents. Does it appear that having chrome accents and being made of wood are independent characteristics? Well, once we have a one of our conditional, we want to provide statistical evidence, we want to compare a marginal distribution to a conditional one. Well, we already have a conditional distribution here, which was the wood given chrome. So if we compare that to the overall of wood, which was 90%, you'll notice that those are almost exactly the same. So we would say there's really no evidence, or it's very weak evidence of an association. So I would call them independent. The conditional probability, which we found here, was 90.7%, which is really close to the marginal of the overall for wood of 90%. So there's no evidence of an association. I believe the characteristics are independent of each other. One way you could say that. Passing the test. Assume that 70% of teenagers who take the written test, driver's license test, study for the test. Of those who study for the test, 95% pass. Those who do not study, only 60% pass. Label the branches of the tree diagram. So the tree diagram is great for conditional probabilities. Our first event is going to be whether or not you studied. And then after that, we'll have the conditional probabilities for those who studied or didn't study for passing or failing. And then if we multiply the probability that you studied times that you passed, that would give us the overall disjoint probability of the intersection of those two, which is those who studied and passed. So they said 70% studied, which means 30% did not. And then of those who studied, 95% passed. That would be the conditional pass rate for those who studied, and meaning 5% failed. And then the pass rate, conditional pass rate for those who did not study was 60%, meaning 40% failed. And then from there we can multiply. So 70% and 95%, that's going to give us the total overall disjoint pass rate. And we can actually fill that in. So studying and passing is going to be the intersection of those two, which is going to be that one right there. And then 5% of 70% is going to be the remaining. So that's going to be 3.5% that studied but did not pass, which would be out here, those unlucky people. Then no study and pass, 30% of 60% is going to give us 18%. So that passed but did not study. And then study but failed is going to be the remaining portion, which would be 12%, which is going to be on the outside of no study and outside of the pass right there. So those are our 4 disjoint probabilities, good to have. Now we're going to do a little bit of conditional probabilities. What's the probability that a teenager who passes the written driver's test did not study? So of those who passed, what's the probability they did not study? So the overall pass rate, if we add those together here and here, it's going to give us, oh, that's right there. Okay, so 84.5%. And then we want to find the intersection for those who did not study and pass, which was the 18%. So it's 18 out of the total that passed, which would give us 21.3%, would be our conditional probability. What's the probability that a student fails the written driver's test? Well, if that was our pass rate, then it would be 1 minus that, or you can just add these two probabilities together, which would be 15.5%, which is what I did. What percent of teens passed the test? That was actually the probability we found there. So we just added those disjoint together. So whether they passed and studied and passed, or passed and didn't study. So add those two together, which will give us the 84.5%. What's the probability a student who fails didn't study? So of those who failed, what's the probability they didn't study? So the fail rate we said was for pass, no pass. Okay, that was the 15.5. And then of those that did not study, so no study and fail would be 12%, which is an overall 77.4%. Does it seem to impact your likelihood of passing driver's test as studying? Okay, so compare marginal to the conditional. Well, if we can compare either one of the the margin or conditional probabilities we found. We'll use the last one. So this was the no study rate given failing. So we want to see and compare that to the overall no study rate, which I believe was 35% or 30%. Yeah, 30%. And that is not anywhere near the probability, the conditional probability of not studying given that you failed. So failing completely changes that probability. Oops, sorry, go back here. So the conditional was 77.4%, which is not close to the marginal for not studying of 30%. So there's strong evidence of association that not studying greatly increases the chances of failing. All right, so that's it for the practice quiz. Let me know if you have any questions. Our first day back, we will take the quiz. So that'll be Tuesday for the A students and Thursday for the B students. So I'll see you guys then. Have a good day.